What if everything around us, the stars in the night sky, the ground beneath our feet, even the screen you're looking at right now, only becomes real because you are here to witness it? This isn't just a wild philosophical guess. It's a question that emerges from the deepest and most baffling discoveries in modern physics. A question that challenges our most basic understanding of existence itself. We are about to take a journey into one of the most profound mysteries of our time, exploring the radical idea that consciousness and observation are not just passive experiences, but might be fundamental forces that shape the very fabric of the cosmos. Think of it as the ultimate version of that classic thought experiment. If a tree falls in a forest and no one is around to hear it, does it make a sound? Now expand that to the entire universe. If a galaxy spins in the vast emptiness of space and no conscious mind is there to perceive it, does it truly exist? The implications of this question are staggering, touching on everything from the nature of time and matter to the ultimate power of our own awareness. To set the stage, let's consider the strange and beautiful world of quantum mechanics, where particles can exist in multiple places at once, behaving as both waves and particles until the moment they are measured. It's as if reality remains a blur of possibilities, a shimmering cloud of maybes, until an observer comes along and pins it down into a single, definite state. This isn't just theoretical, it's been demonstrated in laboratories around the world. Electrons, photons, and other fundamental bits of the universe seem to decide what they are based on whether we are watching. Now take that bizarre quantum rule and scale it up. Apply it not just to a single particle in a lab, but to planets, solar systems, and swirling galaxies. What if the entire cosmic dance only crystallizes into the reality we know because conscious beings are here to see it? The idea that we, as observers, might be co-creators of the universe is both humbling and electrifying, suggesting that our role in the cosmos is far more active and significant than we ever imagined. So, throughout this video, we will dive into the heart of this epic exploration. We'll trace the origins of this mind-bending concept from the early days of quantum theory with pioneers like Niels Bohr and Werner Heisenberg, to the modern interpretations that continue to push the boundaries of what we think is possible. We'll examine the compelling evidence, the fierce debates, and the breathtaking implications of a universe that might literally be waiting for us to look at it in order to become real. This is a story about the power of perception, the nature of existence, and the incredible possibility that each of us plays a vital part in the ongoing creation of everything that is. So get comfortable, open your mind, and prepare to question everything you thought you knew about reality. What you are about to discover could change the way you see yourself and your place in the cosmos forever. For centuries, our understanding of the cosmos was built on a foundation of reassuring certainty. This was the era of classical physics, a worldview championed by figures like Isaac Newton, which portrayed the universe as a vast and magnificent clockwork mechanism. Imagine the solar system as an immense, intricate timepiece, with planets following their orbital paths with unwavering precision, governed by the immutable force of gravity. An apple falls from a tree not because it chooses to, but because it is compelled by a set of unbreakable mathematical laws. In this grand scheme, every object from the tiniest pebble to the largest star had a definite position and a definite velocity at any given moment. Reality was considered to be objective and absolute, existing completely independently of any human perception. The cosmos was simply there, a fully formed, predetermined reality that would continue to tick along with or without a conscious mind to witness its operation. This perspective created a very clean and comforting separation between us, the observers, and the world we were observing. We were merely spectators in a cosmic theater, watching a play that would go on exactly the same whether we were in the audience or not. This deterministic framework was so powerful and so successful at predicting everything from the tides to the trajectories of cannonballs that it dominated scientific thought for over 200 years, cementing the idea of a universe that was both predictable and utterly detached from the act of observation itself. But this comforting, predictable universe was about to be turned completely on its head. The dawn of the 20th century ushered in a scientific revolution so profound that it shattered the very foundations of that classical clockwork, revealing a hidden realm of breathtaking strangeness operating just beneath the surface of our everyday experience. This was the birth of quantum mechanics, and its pioneers, figures like Albert Einstein, Niels Bohr, and Werner Heisenberg, were about to uncover rules of reality that defied all common sense. The central, shocking discovery was this: when you peer into the heart of matter, into the realm of atoms and the particles that constitute them, the clear-cut certainties of Newton's world simply vanish. An electron, for instance, does not travel along a single, neat path from one point to another. Instead, it exists as a blur of possibilities, a spread-out wave of potential locations, speeds, and even states of being, all at the same time. It is only at the precise moment someone makes a measurement, the instant an observation is made, that this fuzzy cloud of potentialities collapses into a single, definite particle with a specific position. Before that measurement, the question, "Where is the electron?" has no single answer. It is quite literally everywhere it could possibly be, all at once. This phenomenon, known as superposition, was a direct and brutal challenge to the classical idea of an objective reality existing independently of us. The universe, it seemed, was not a collection of definite objects, but a vast ocean of probabilities. And the act of observation was not a passive glance, but an active participant, a force that reached into this ocean of maybe and compelled it to become a solid this. The implications were immediately staggering. It suggested that the bedrock of physical reality was not solid matter, but information and potentiality, and that consciousness, through the simple act of looking, might be the mysterious ingredient that transforms that potential into the concrete world we all share. This was the first crack in the dam of classical thought, a small, subatomic whisper that would grow into a roar, questioning whether anything is truly real until it is seen. This stunning shift from a predictable clockwork to a bizarre world of probability found its most powerful and iconic demonstration in a deceptively simple setup known as the double-slit experiment. To truly grasp the depth of the mystery we're exploring, we need to take a close look at this foundational moment, because what it reveals is so strange that it feels more like magic than science. Picture a standard wave, like a ripple in a pond. If you put a barrier in the water with two openings, the ripples will spread out from each slit, and where those two sets of ripples meet, they will interfere with each other. In some places, a peak from one wave will meet a peak from another, creating an even bigger peak. This is called constructive interference. In other places, a peak will meet a trough, and they will cancel each other out. This is destructive interference. The result is a distinct pattern of alternating bright and dark bands on a screen behind the barrier, a classic signature of wave behavior. Now let's switch from water waves to light. For a long time, scientists argued whether light was made of particles or waves. When they performed the double-slit experiment with light, they saw that same telltale interference pattern, confirming that light indeed behaves as a wave, spreading out and interacting with itself. Here is where the plot thickens enormously. Scientists decided to fire not waves of light, but single, individual particles like electrons at the double-slit barrier, one electron at a time. You would logically expect each electron to pass through one slit or the other, and then hit the screen directly behind that slit, building up two bright bands directly in line with the two openings. But that is not what happens, not even close, when you fire these particles one by one, and you do not try to observe which slit they go through. They do not form two bands. Instead, over time, they build up that same interference pattern of multiple bands. as if each individual electron is somehow passing through both slits at the same time and interfering with itself. It's as if you were throwing individual marbles at a wall with two holes, and instead of piling up in two spots behind the holes, they arranged themselves into a striped pattern, as if each marble had turned into a wave, gone through both holes, and then interfered with its own path before deciding where to land. This is the heart of quantum weirdness. A single particle exists in a state of superposition, effectively being in multiple places and following multiple paths simultaneously, behaving not as a solid object but as a wave of probability. Then comes the moment that changes everything and directly gives rise to our central question about observers creating reality. The scientists then added a measuring device right by the slits to detect which specific slit each electron actually passes through. The instant they did this, the very moment they tried to pin down the electron's path and make an observation, the incredible interference pattern vanished. The electrons stopped behaving like spread-out waves and started behaving like ordinary particles. They went back to forming two simple, predictable bands on the screen, as if they were tiny bullets that had chosen one slit or the other. It wasn't the physical effect of the detector that caused this change. It was the act of obtaining information, the act of measurement itself. The universe, at its most fundamental level, seemed to be aware that it was being watched, and it changed its behavior accordingly. When no one is looking, an electron is a blurry cloud of potential, exploring all possible paths. But the second a conscious mind sets up an apparatus to ask, which path are you on? The electron snaps to attention, picks a single, definite history, and acts like a well-behaved little particle. This forces us to confront a truly radical possibility. Is the wave function, this mathematical description of all possible states, not just a calculation tool but the true, fluid reality? And is the particle's definite existence merely a single item selected from this vast cosmic menu of possibilities only when a conscious being places an order by looking at it? The double-slit experiment stands as a monumental pillar of evidence suggesting that the answer might be yes, and that our role in the universe is far more active and creative than we ever dreamed. Out of this quantum revolution emerged the first and most influential framework for making sense of the madness, the Copenhagen interpretation, primarily shaped by the minds of Niels Bohr and Werner Heisenberg. This wasn't just a minor adjustment to physics, it was a radical philosophical stance that placed the observer squarely at the center of the cosmic drama. Bohr and Heisenberg argued that it is meaningless to talk about a quantum particle having any definite properties at all before it is measured. An electron does not have a specific position or a specific momentum. It exists in a ghostly state of pure potential, described mathematically by the wave function. This wave function isn't just a representation of our ignorance. It is the complete description of the system's reality, a reality that is fluid, probabilistic, and fundamentally undefined. The definitive properties we associate with the physical world simply do not exist until the very moment an observation is made. It is the act of measurement itself that forces the system to make a choice, causing the wave function to collapse from a haze of could be into a single concrete is. A powerful, everyday analogy can help make this abstract idea feel much more tangible. Imagine you have a special coin that is perpetually spinning on its edge. While it's spinning, it isn't heads and it isn't tails. In fact, the question, what side is facing up, has no real answer. The coin exists in a superposition of both states simultaneously. It is only when you slam your hand down on the coin, stopping its spin and looking at the result, that it becomes definitively heads or tails. The Copenhagen interpretation applies this exact logic to the entire quantum realm. The spinning coin is the wave function, the realm of possibility. Your act of slapping your hand down and looking is the measurement, and the final, settled state of the coin is the collapsed reality we then perceive. Prior to your observation, the coin wasn't secretly heads the whole time. its very identity was unresolved, waiting for your interaction to finalize it. This is the profound and for some deeply unsettling core of the Copenhagen view. The universe at its most fundamental level remains in a state of unresolved potentiality until a conscious observation crystallizes it into the solid world we experience. This interpretation, however, immediately raises a massive and perplexing question: what or who qualifies as an observer? Is it a sophisticated laboratory instrument with flashing lights and digital readouts? Or does it require the conscious awareness of a human scientist to finally read that readout? The founders of the Copenhagen interpretation were somewhat deliberately vague on this crucial point, creating a boundary that has fueled debate for decades. If a Geiger counter clicks, registering the decay of a radioactive atom, has the wave function collapsed? Or does it only truly collapse when a graduate student, sipping coffee in the lab, hears that click and becomes consciously aware of the result? This ambiguity leads us to the edge of a profound mystery, suggesting that consciousness itself might not be an accidental byproduct of the brain, but a fundamental component of the universe's operating system. The Copenhagen interpretation doesn't just give us a new set of physical laws. It hands us a mirror, forcing us to consider that our own awareness might be the mysterious, active ingredient that completes the reality we inhabit. It proposes that we are not just living in the universe, but that we are in a constant, dynamic dance with it, participating in the ongoing creation of everything we see, touch, and know. Now, just as this new quantum worldview was taking hold, a brilliant physicist named Erwin Schrödinger decided to craft a thought experiment that would push these ideas to their absolute limit, revealing what he saw as a profound and almost comical absurdity. He wanted to expose the strange consequence of claiming that observation collapses reality, and he did so with a scenario involving a rather unfortunate feline. Picture, if you will, a perfectly ordinary cat. Let's call him Felix. Felix is placed inside a perfectly sealed steel box. Alongside him in the box is a tiny, minuscule amount of a radioactive substance. There is a detector aimed at this substance, and if it detects that a single atom from this material has decayed a purely random quantum event, the detector triggers a mechanism that releases a deadly poison into the box. Now, here's the crucial quantum rule we just learned. According to the Copenhagen interpretation, that radioactive atom exists in a superposition. It is in a state where it has both decayed and not decayed simultaneously. Its wave function contains both possibilities. This means the detector is also in a superposition, both triggered and not triggered. Consequently, the poison vial is both broken and intact. And this leads to the inescapable and deeply strange conclusion. Until someone opens the box and looks inside, the cat itself must be considered both alive and dead at the very same time. It's not that we don't know whether the cat is alive or dead. The theory insists the cat is genuinely in a blurred state of existence, a grotesque mixture of a purring pet and a deceased one, until the act of observation forces the entire system to choose one definitive history. Schrödinger presented this not as a serious proposal, but as a kind of intellectual protest. His point was to show how ridiculous it seemed to take the bizarre rules of the tiny quantum world and apply them directly to the large, warm, furry world of our everyday experience. He was essentially saying to his colleagues, look, your interpretation leads to this, a cat that is both alive and dead. That's nonsense. Something must be wrong with a theory that allows for such a paradoxical reality. He intended his cat to be a reductio ad absurdum. An argument that demonstrates a theory is false by showing it leads to an absurd result. For Schrödinger, the idea that a conscious observer was needed to kill or save the cat was philosophically monstrous. He believed reality should be independent of us. The cat should be either alive or dead based on the physical events inside the box, regardless of whether a physicist was peeking in or not. The cat, he argued, or the air in the box or the detector itself, should be capable of causing the wave function to collapse without requiring a human mind. His thought experiment was a powerful challenge designed to force the physics community to confront the sheer strangeness of what they were proposing. Yet, in a wonderful twist of intellectual history, Schrödinger's cat broke free from its creator's original intent. Instead of burying the Copenhagen interpretation, the paradox became its most famous and enduring symbol. The vivid, almost unsettling image of a cat in a ghostly state between life and death captured the public imagination and cemented the observer effect into popular culture. It became the perfect, if exaggerated, illustration of the central question: where do we draw the line? If a single electron exists in a superposition until measured, why not a collection of atoms? Why not a detector? Why not a vial of poison? And if all those things can be in a superposition, why not a cat? The thought experiment brilliantly highlights the measurement problem, the deep and unresolved puzzle of what exactly constitutes a measurement and when the collapse from probability to reality actually occurs. It forced everyone to grapple with the boundary between the quantum and the classical worlds. The cat in the box became more than just a punchline to a physics joke. It became a profound philosophical tool, a constant reminder that our attempts to describe reality at its most fundamental level lead us into a territory where logic as we know it seems to break down, and where the simple act of looking might hold a power we are only just beginning to comprehend. But what if the observer isn't alone in the room? What happens when we have a whole chain of observers, one inside the experiment and one outside, each with their own private reality? This is precisely the brilliant and mind-warping paradox introduced by physicist Eugene Wigner, taking the puzzle of Schrödinger's cat and extending it into the social realm of shared knowledge. Let's set the scene. Imagine Wigner has a friend, a trusted, capable fellow physicist. This friend enters a sealed laboratory, equipped to perform the exact kind of quantum experiment we've been discussing, perhaps one with a single particle in a superposition. The friend carefully sets up the apparatus, runs the experiment, and looks at the result. From the friend's perspective inside the lab, the measurement has been made, the wave function has collapsed, and the result is now a definite fact. He has seen the particle in one specific state, and he has written the outcome in his lab notebook. He knows what happened. Now, let's step outside the laboratory door where Eugene Wigner himself is waiting. From Wigner's external perspective, the entire laboratory, including his friend, the equipment, and the notebook, is still just a quantum system. He hasn't made an observation yet. According to the strict Copenhagen rules, until Wigner opens the door and asks his friend what he saw, the entire contents of that room must be described by a single, gigantic wave function. This means that for Wigner, his friend is not yet in a definite state of having seen one result. His friend is in a superposition of having seen result A and having seen result B simultaneously. The lab notebook itself is in a superposition of having both outcomes written on its page. The entire sequence of events inside the room remains an unresolved potential until the moment Wigner interacts with it by asking the question. So we are left with a profound and deeply personal contradiction. The friend inside is absolutely certain of a single outcome. He has a clear memory of performing the experiment and seeing the result. But for Wigner outside, his friend has no such single memory yet. His friend's very consciousness is suspended in a blur of possibilities. This thought experiment pushes the role of consciousness to the forefront in a way that Schrödinger's cat never did. It forces us to ask an incredibly direct question: whose observation counts? Is it the first conscious awareness that touches the quantum system, which in this case is the friend's? Or is it the final awareness that incorporates that information into a larger worldview, which is Wigner's? If we side with the friend, then the wave function collapses the moment he looks at the instrument, and Wigner's perspective is simply one of ignorance about a fact that is already settled. But if we side with Wigner, then we are forced to accept a truly staggering conclusion, that a conscious human being with thoughts and memories can be placed into a state of quantum superposition, his mind split between two different experiences until another conscious mind decides to look at him. This isn't just about a cat in a box anymore, it's about the sanctity of individual conscious experience itself. Wigner himself leaned toward this radical view. He speculated that it is indeed the consciousness of the observer that causes the collapse of the wave function. In his view, the friend's consciousness wasn't sufficient to finalize reality. It was only when his own mind received the information that the entire entangled system of friend and lab snapped into a single, consistent history. The implications of Wigner's friend ripple outwards, creating endless puzzles. If Wigner's observation collapses the reality for his friend, what happens when Wigner then tells his wife about the result? Does her consciousness then collapse a wave function that included Wigner? This suggests an infinite regress of observers, a chain of conscious acts needed to solidify the universe, which seems philosophically messy and deeply unsatisfying. The paradox highlights the core of the measurement problem with terrifying clarity. We have no scientific definition for what constitutes a measurement, and we have no clear boundary between what can exist in a superposition and what cannot. Can a single atom be in a superposition? The double-slit experiment says yes. Can a cat be in a superposition? Schrödinger said that idea is absurd. Can a human mind be in a superposition? Wigner's friend forces us to consider that it might be possible, leading us into a realm where physics and philosophy become inextricably linked, and where the nature of our own awareness becomes the ultimate mystery. Faced with the deeply personal paradoxes of Wigner and his friend, a different kind of mind sought a way out, a solution so elegant and yet so audacious that it would reframe the entire cosmic conversation. In the 1950s, a young physicist named Hugh Everett Roman III proposed a radical alternative to the Copenhagen dogma, one that did away with the mysterious collapse of the wave function and, in a single stroke, removed the observer from its privileged pedestal. His idea, known as the many worlds interpretation, suggests a breathtaking revision of reality. The wave function never collapses at all. Instead, every single possible outcome of a quantum event actually happens. When an electron is measured, it doesn't randomly pick one position from its cloud of possibilities. It manifests in all of them simultaneously. The catch is that each possibility plays out in a newly branched, parallel universe that is just as real and physically concrete as our own. Think of reality not as a single, linear path, but as an impossibly vast, forever forking tree. At the moment of any quantum event, a particle's path, the decay of an atom, even the random firing of a neuron in your brain, the universe doesn't make a choice. It makes every choice. One branch of the tree is the universe where the electron went left. Another, equally valid branch is the universe where it went right. In the context of Schrödinger's famous cat, this means there is no monstrous superposition of a half-dead, half-alive animal. At the moment the radioactive atom's fate is tied to the cat's life, the universe cleanly splits in two. In one universe, the atom decays, the poison is released, and the cat dies. In the other, perfectly real and separate universe, the atom does not decay, the poison remains contained, and the cat lives on, blissfully unaware of its alternate demise. Both histories are real, they just unfold in different, non-communicating branches of the cosmic tree. In this view, the act of measurement isn't a special event that forces a collapse, it's merely the moment an observer becomes aware of which branch they are on. The observer themselves splits along with the rest of the universe, with one version of them seeing one result and another version seeing the other. This interpretation offers a powerful and compelling answer to the puzzles we've encountered. It completely sidesteps the thorny measurement problem by declaring that measurement is just another physical interaction, governed by the same quantum rules as everything else. There is no longer a need to define what qualifies as an observer or when consciousness triggers a collapse, because nothing ever collapses. The wave function simply evolves smoothly and deterministically, with every possibility being realized in its own world. Wigner's friend paradox also dissolves beautifully. From Wigner's perspective outside the lab, his friend does enter a superposition, but this is simply a description of the friend becoming entangled with the quantum system. When Wigner eventually opens the door, he doesn't cause a collapse. He himself becomes entangled with the larger system. He interacts with his friend and splits into multiple versions. One Wigner hears his friend excitedly report that he saw result A, while another, equally real Wigner hears the same friend report that he saw result B. Both conversations are genuine and both sets of memories are valid. They just exist in parallel streams of reality. While this solves some profound problems, the implications are, to put it mildly, mind-boggling. The cost of this elegant solution is a reality of almost unimaginable plurality. Every trivial quantum event, every random fluctuation, every decision that involves the slightest quantum uncertainty spawns new universes. This means there isn't just one universe where you are watching this video. There are countless others. There is a universe where you decided to click on a different video today. There is a universe where the company that built your device used a slightly different arrangement of atoms in a transistor, changing its performance. There is a universe where a cosmic ray struck the Earth's atmosphere a millisecond differently, leading to a chain of events that altered human history. The number of parallel worlds is not just large, it is infinite, with new branches splitting off from every existing branch at every possible moment. This isn't a multiverse of vague potential. It is a multiverse of concrete, physical reality, where every possible version of every possible story is being told somewhere. The many worlds interpretation presents us with a cosmos of breathtaking scope and profound loneliness, suggesting that every possibility is not only imagined but is lived out in full, even as we remain consciously aware of only a single, unfolding thread in the infinite tapestry of existence. While the many worlds interpretation offers a dazzling escape from the paradoxes of observers and cats, it asks us to accept an infinite, branching reality that can feel more like science fiction than testable science. This tension between the profoundly weird and the intuitively physical has driven physicists to search for a bridge, a mechanism that explains why our everyday world feels so solid and definite, even as its quantum foundations remain so fluid. This search leads us to a powerful and now widely accepted concept known as quantum decoherence, a modern perspective that grounds the transition from the quantum to the classical in the simple, relentless interactions of the physical world. The central, elegant idea of decoherence is this: a quantum system doesn't need a conscious observer to collapse its wave function. Instead, it loses its quantum magic, its superposition and interference, simply by bumping into its surroundings. Think of a perfectly still, pristine pond. If you place a single drop of ink on its surface, you can watch its perfect, circular form. This is like an isolated quantum system in a pure superposition. But now, imagine that pond is not still. It's being constantly jostled by wind, by rain, by tiny currents. The moment that perfect ink drop hits the water, it immediately begins to spread out, its distinct form rapidly mixing and blurring with the surrounding liquid until it becomes an indistinguishable, uniform shade. The information about the ink drop's original, precise state is not destroyed. It is carried away, dissipated into the vast number of particles in the environment. It becomes irretrievably lost in the crowd. This is precisely what happens to a quantum system. The moment it interacts with even a single photon of light or a molecule of air, its delicate state of superposition, its quantum coherence, is scattered into the environment. The system becomes entangled with countless other particles, and from our limited local perspective, it appears to have chosen a single classical state. The famous interference pattern in the double-slit experiment vanishes not because a conscious mind is watching, but because the electrons are being constantly buffeted by their environment, which constantly records which path they took, destroying their wave-like behavior. This process of decoherence happens with staggering speed and is utterly unavoidable. To maintain a quantum superposition, a system must be almost perfectly isolated from the outside world. For a single electron or a tiny atom, this is possible in a high-tech laboratory vacuum cooled to near absolute zero. But for anything larger, a dust mote, a virus, a cat, it becomes practically impossible. A household cat, for instance, is constantly bathed in the warm glow of trillions upon trillions of infrared photons, its body vibrating with thermal energy, its molecules colliding with air. In less than a tiny fraction of a nanosecond, any quantum superposition the cat could theoretically be in would be completely washed away by this decoherence. The environment acts as a continuous, unconscious observer, constantly measuring the system and forcing it to behave in a classical way. This provides a powerful physical explanation for why we don't see cats that are both alive and dead. It's not that the superposition is impossible in principle. It's that for any object large and warm enough to be a cat, decoherence makes that superposition so fleeting and unstable that it is over before it could ever be noticed. The environment, in a very real sense, selects the classical reality we experience by instantly destroying the quantum alternatives. So, what does decoherence mean for the role of the conscious observer? Does it finally dethrone consciousness from its central role in creating reality? The answer is nuanced and fascinating. Decoherence brilliantly explains how the quantum world appears classical to us. It describes the mechanism by which superpositions become unobservable and why definite properties emerge. However, most physicists argue that decoherence does not entirely solve the deeper philosophical measurement problem. It explains why we see a definite outcome, but it doesn't necessarily explain why only one outcome exists in our experience. In the language of the wave function, decoherence describes how different possibilities become effectively separated from one another, but it doesn't make the other possibilities go away. From a many-worlds perspective, decoherence is precisely the process that defines the branching of the universes, cleanly separating the parallel worlds so they no longer interfere. From a more traditional viewpoint, decoherence makes the wave function look like it has collapsed from our perspective, even if the underlying quantum reality remains full of potential. In this way, decoherence doesn't so much remove the observer as it relocates them. The observer is no longer a mystical collapse trigger, but a complex classical system that is itself subject to decoherence. Our brains, our measuring devices, are all part of this entangled, decoherent world. We don't cause the collapse, we are simply caught up in the same relentless process that makes the entire macroscopic world behave classically. We are products of a reality that has already been clarified and defined by its constant conversation with itself. This modern understanding brings a new kind of humility, suggesting that the definite world we perceive is not a special creation of our minds, but the inevitable and noisy outcome of a universe where nothing, not even a single particle, can ever truly be alone. So where does this leave us in our quest to understand the observer? We've seen how decoherence provides a physical mechanism for the emergence of a classical world, but it still doesn't fully answer the deep, lingering question of experience. Why is there a subjective, first-person view associated with any of these physical processes? This is what philosopher David Chalmers famously termed the hard problem of consciousness. It's one thing to explain how the brain processes information, integrates data, and controls behavior. These are the easy problems. But it's an entirely different challenge to explain why and how all that intricate neural activity gives rise to the inner movie of conscious awareness, the taste of chocolate, the feeling of awe, the simple sensation of the color red. This profound mystery forces us to shift our gaze from the pure physics of measurement to the philosophy of mind, and to consider a possibility that once seemed relegated to the fringes, that consciousness itself might be a fundamental feature of the universe as basic as space and time. This line of thinking brings us back to the brilliant Hungarian-American polymath John von Neumann. In his groundbreaking work, The Mathematical Foundations of Quantum Mechanics, von Neumann took the logical structure of the theory to its ultimate conclusion. He argued that the entire chain of measurement from the quantum system to the detector to the physicist's brain could be viewed as one continuous quantum system. There is no clear physical line where the wave function magically collapses, so if we follow the math, von Neumann proposed that the collapse must happen at the final link in the chain, the conscious mind of the observer. In this view, consciousness is not an emergent illusion produced by a complex brain. It is the very thing that completes reality. The physical world remains in a state of shimmering potential until it is registered by an immaterial consciousness, which acts as a kind of ultimate arbiter, selecting one reality from the menu of possibilities. This places consciousness not as a passive byproduct, but as an active, non-physical participant without which the universe would remain an undefined haze of probabilities. Building on this radical foundation, the renowned physicist and mathematician Roger Penrose introduced an equally provocative theory, one that seeks to ground this active role of consciousness in a new kind of physics. Penrose, collaborating with anesthesiologist Stuart Hameroff, proposed that consciousness arises from quantum processes happening within the brain's neurons, specifically within structures called microtubules. Their theory, known as orchestrated objective reduction, suggests that these microtubules can maintain quantum superpositions, but only for a very short time. What causes the collapse, according to Penrose, is not random chance or environmental interaction, but a fundamental threshold related to the mathematics of gravity. When the superposition states in the brain reach a certain level of self-colliding reality, they objectively reduce to a single state, and it is this moment of quantum collapse that gives rise to a conscious thought. In this framework, consciousness is not causing the collapse in the von Neumann sense. Rather, each conscious moment is a collapse, a quantum gravitational event occurring in the fabric of the brain. This provides a potential bridge, suggesting that the mind is not separate from the quantum world, but is an exquisite manifestation of its most fundamental processes. These theories, while speculative, point toward a universe that is far more integrated and mind-like than the cold, mechanical cosmos of classical physics. They invite us to consider a truly grand possibility, that the universe is not merely observed by consciousness, but that it is conscious in some fundamental way. Could it be that the cosmos is awakening to itself through us, that we are not just insignificant specks in a vast, indifferent void, but are instead the sense organs of a universe that is slowly becoming self-aware? Our human minds, with their capacity for wonder, love, and curiosity, might be the means by which the cosmos reflects upon its own beauty and mystery. This idea, often found in spiritual traditions, finds a strange and compelling echo in these modern scientific speculations. It suggests a cosmic symbiosis. The universe provides the physical stage and the quantum rules, and we, as conscious beings, provide the observation that gives that stage its form and substance. We are not just living in the universe is living through us, experiencing the drama of existence from a near infinite number of points of view. This perspective doesn't provide easy answers, but it beautifully reframes the ultimate question, transforming our search for meaning from a lonely human endeavor into a central part of the universe's own great unfolding story. Now let's pull our gaze back from the quantum realm and expand it to the scale of the entire cosmos, because the mystery of the observer doesn't end with particles in a lab. In fact, it finds a stunning, large-scale echo in the very structure of the universe itself. This brings us to a profound and deeply provocative idea known as the Anthropic Principle. At its heart, this principle confronts a series of breathtaking coincidences that physicists and cosmologists have uncovered. They've found that the universe appears to be exquisitely fine-tuned for life, with its fundamental constants and forces balanced on a razor's edge. Imagine you are setting up the parameters for a universe. You have a cosmic control panel with dials for things like the strength of gravity, the force that holds atomic nuclei together, the mass of an electron, and the amount of dark energy causing the universe to expand. Now, if you were to tweak any one of these dials even slightly, just a fraction of a percent, the consequences would be catastrophic. A little stronger gravitational constant, and the universe would have collapsed back on itself moments after the Big Bang. A little weaker nuclear force, and hydrogen would never have fused into heavier elements, meaning no carbon, no oxygen, and no chemistry of life. If the electron were a tiny bit heavier or lighter, atoms couldn't form stable structures. It's as if someone set all these dials to unbelievably precise values that just so happen to allow for the eventual emergence of stars, planets, and conscious beings like us who can look up and wonder about it all. This astonishing fine-tuning leads directly to the two main versions of the Anthropic Principle, which offer different ways of interpreting what this cosmic coincidence means. The first, known as the weak Anthropic Principle, takes a more observational and almost tautological stance. It simply states that we must find ourselves in a universe capable of supporting our existence, because if we didn't, we wouldn't be here to notice. It's a statement about selection bias. Consider a puddle of water waking up one morning and marveling at how perfectly the hole it sits in conforms to its shape. The puddle thinks, "This hole fits me exactly. It must have been designed just for me." But of course, the reality is the other way around. The puddle adapted to the shape of the hole. Similarly, the weak Anthropic Principle suggests that we are the puddle. We shouldn't be surprised that the universe we observe has properties that allow for observers, because we couldn't observe one that didn't. It doesn't explain why this particular universe exists. It just notes that our ability to ask the question is conditional on being in a universe that permits our existence in the first place. Then there is the more provocative strong Anthropic Principle. This version goes a significant step further, proposing that the universe must have properties that allow life to develop at some stage in its history. This isn't just about our lucky position. It's a statement about the necessary conditions for any universe at all. The strong version ventures into much deeper philosophical and even metaphysical territory, hinting that the emergence of conscious observers might be a fundamental requirement of the cosmos, somehow written into the laws of physics from the very beginning. It raises the possibility that the universe and the observer are not separate entities, but are inextricably linked parts of a single, coherent system. In this view, the constants are fine-tuned not by random chance, but because a universe without the potential for consciousness might be incomplete or even impossible. This begins to sound remarkably like the quantum principle we explored earlier, but now writ across the vast canvas of the entire cosmos. Just as a quantum particle seems to need an observer to pin down its reality, the cosmos itself, with its finely tuned laws, might also require observers to give it meaning and definition. The universe develops the potential for life, and life, in turn, through the act of observation, completes the universe. When we connect the dots between the Anthropic Principle and our earlier quantum discussions, a truly grand and symbiotic picture starts to emerge. It suggests a cosmic dance between the very large and the very small, a profound connection between the conditions that allow for life and the role that life plays in shaping reality. The universe, through an unimaginably precise set of physical laws, sets the stage, creating galaxies, forging stars, and cooking up the complex elements necessary for biology. Then, on at least one small planet around a stable star, conscious beings evolve. These beings, armed with awareness, begin to look back at the universe. They perform double-slit experiments and ponder cosmological constants. And in that very act of observation, they are not just passive recipients of a preordained reality. They are active participants, collapsing quantum probabilities and, in a sense, affirming the universe's own existence. The fine-tuning allows for the observer, and the observer, through the act of perception, might be what actualizes the fine-tuned universe. This creates a beautiful, self-referential loop, a universe tailored for life, and life that in turn gives the universe its defined form. It transforms the cosmos from a cold, mechanical artifact into something that seems almost alive, a system that has the potential for self-awareness woven into its very fabric. We are not accidental tourists in an indifferent universe. We may be an essential part of its very nature, the means by which the cosmos comes to know and experience itself. This journey into the quantum observer and the fine-tuned cosmos leads us to one of the most visionary physicists of the 20th century, John Archibald Wheeler, who took these ideas and forged them into a truly cosmic principle. Wheeler, who had a hand in coining the term black hole, was never one to shy away from the biggest questions. He looked at the quantum mystery and the anthropic puzzle and saw them not as separate issues but as two sides of the same profound coin. He proposed what he called the participatory anthropic principle, a concept that elevates the observer's role from a mere participant to a fundamental necessity for the very existence of the universe. In Wheeler's grand vision, the universe could not come into being in a full and meaningful way without the presence of conscious life to observe it. It's a staggering inversion of our usual logic. We tend to think of the universe as a finished product that eventually and accidentally produced us. Wheeler suggested the opposite, that the universe is a self-excited circuit, a loop in which it gives rise to observers, and those observers, through the very act of observation, bring the universe into tangible existence. We are not just living in the universe, we are the universe completing a cycle of self-awareness, essential players in making reality real. To grasp the mechanics of how this could possibly work, we need to dive into Wheeler's famous slogan, "It from bit." This phrase encapsulates a radical shift in what we consider to be the most fundamental substance of reality. For centuries, we've believed in a universe made of its tangible stuff like matter and energy. Wheeler proposed that at the very bottom, beneath the quarks and the electrons, the ultimate foundation is not matter but information. The "its" of the physical world are actually derived from bits, the binary yes or no answers given by quantum measurements. Think of reality not as a collection of solid objects, but as an immense cosmic computer that is constantly processing information. Every elementary particle, every force field, is ultimately a manifestation of an immense number of binary responses to an immense number of quantum questions. When you ask a quantum question like, "Is this electron here or there?" the universe doesn't consult a pre-existing reality to find the answer. Instead, the act of asking the question, the act of making an observation, generates the answer, and that answer is the reality. The definite location of the electron doesn't exist until the measurement produces the informational bit that says, "Here." In this view, every observation is a fundamental creative act, a moment where the universe concretizes from a sea of potential information into a specific classical fact. The physical world we move through is a grand tapestry woven from countless such informational threads, all summoned into being by the participatory act of looking. Wheeler, being a master of thought experiments, didn't stop there. He wanted to push this idea to its absolute limit, to demonstrate just how deep the rabbit hole goes. He devised a stunning scenario called the delayed choice experiment, which takes the quantum weirdness of the double slit and scales it up to a cosmic level, with implications that shake our understanding of time itself. Imagine a distant quasar, a brilliant source of light billions of light years away. Between that quasar and our telescope here on Earth, there is a massive galaxy. According to Einstein's theory of general relativity, the gravity of this galaxy will bend the space around it, acting like a giant lens. This means the light from the quasar can take two different paths around the galaxy to reach us. Now we can set up a detector to capture this light in two different ways, mirroring the classic double-slit experiment. We can choose to measure the light in a way that forces it to reveal which path it took, like putting a detector at each of the two cosmic slits. When we do this, we see two distinct images of the quasar. Or we can set up our equipment to produce an interference pattern, which would only be possible if the light traveled as a wave, taking both paths simultaneously and interfering with itself. Here is Wheeler's brilliant and mind-bending twist. The light from that quasar began its journey billions of years ago. It has been traveling through space for eons, long before humans even existed, let alone built telescopes. According to our everyday logic, that light should have decided whether it was taking one path or both paths way back then, at the very beginning of its journey. But Wheeler's delayed choice experiment shows that this is not the case. We today get to decide how we want to measure that ancient light, and our choice today, made billions of years after the photon began its voyage, determines the past behavior of that photon. If we choose to measure for a particle path, we force the photon to have taken one definite path billions of years ago. If we choose to measure for wave interference, we force that same photon to have taken both paths simultaneously all those eons in the past. Our observation in the present is retroactively determining the history of the universe. It's as if the universe, until the moment of observation, exists in a state of unresolved history, a cloud of potential pasts, and it is only when a conscious observer makes a measurement that a single, consistent timeline snaps into place, reaching all the way back to the beginning. Visualize this as a vast, unfinished tapestry of cosmic history. The threads are all there, but the pattern is not yet fixed. It remains a blur of possibilities, a story waiting to be told. We, as observers here and now, are the ones who, by the questions we choose to ask and the measurements we choose to make, finally weave those threads into a coherent and definite picture. We are not just reading the book of the universe, we are writing its chapters with every glance. This is the ultimate expression of Wheeler's participatory vision, a universe that is not a pre-recorded film but an interactive, ongoing creation, where our present acts of observation reach back across time to sculpt the very past that led to our existence. It's a concept that challenges the core of our intuition, suggesting that we are not passive products of a fixed history, but active architects of a reality whose foundations are being laid down with every single observation we make. But if consciousness truly is this fundamental force, this ultimate arbiter of reality, where does it actually come from? We've explored theories that place it at the apex of a measurement chain, but this still leaves us with a kind of cosmic chicken and egg problem. Did consciousness simply emerge from the random, complex arrangement of dumb matter in the human brain? Or could it be something that was present all along, woven into the very fabric of existence from the very first moment? This brings us to one of the most ancient and, in modern times, one of the most resurgent philosophical ideas for addressing the hard problem, panpsychism. The term itself comes from the Greek words pan, meaning all, and psyche, meaning soul or mind. In its simplest form, panpsychism proposes that consciousness is not a late-arriving miracle in a previously unconscious universe. Instead, it suggests that mind, or at least a raw capacity for experience, is a fundamental and ubiquitous feature of all physical matter. Just as electrons possess properties like mass and charge, they might also possess an intrinsic, albeit incredibly simple, form of interiority, a raw feeling of being. This isn't to say that an electron is thinking deep thoughts or pondering the meaning of life. The proposal is far more subtle and strange. It posits that even the most basic building blocks of reality have a minute, elemental form of experience often called proto-consciousness. This proto-consciousness isn't complex thought or self-awareness. It's more like the most basic unit of sensation, a single, isolated note of experience, perhaps something as simple as the faintest whisper of being. To understand this better, consider the property of mass. We don't ask how a collection of massless particles can somehow come together to create mass. Mass is just a fundamental property that certain particles have. Panpsychism asks us to consider consciousness in the same light. The problem of how unconscious matter arranged in a certain way suddenly sparks into conscious awareness. The so-called hard problem is, from the panpsychist view, a category error. It's like wondering how you can assemble a bunch of colorless particles to create the color red. If consciousness is already a fundamental property, then the question shifts. The mystery is no longer how consciousness emerges from matter, but how these tiny, fundamental specks of proto-consciousness combine and integrate to form the rich, unified, and complex stream of awareness that you and I experience every moment. Your conscious mind, in this view, isn't a ghost that suddenly appeared in the machine of your brain. It is a vast, orchestrated symphony composed of trillions upon trillions of these tiny mental notes, each contributed by the fundamental particles that make up your neurons, integrated through the brain's unfathomably complex network into the single, seamless melody of yourself. Now, let's connect this philosophical framework back to our central theme of the observer. If panpsychism is even remotely true, it offers a breathtakingly elegant solution to the quantum measurement problem. The question of what qualifies as an observer suddenly becomes much less mysterious. The universe doesn't need a highly evolved human brain to collapse a wave function because the universe is already, at its most fundamental level, awake and aware. Every single interaction between particles from the moment of the Big Bang could be seen as a form of observation. When an electron interacts with a photon, the electron is, in its own primitive way, observing the photon, and the photon is observing the electron. This constant, buzzing network of mutual interaction among fundamentally conscious entities is what solidifies reality from the quantum ground up. The cosmos is not a cold, empty void waiting for us to give it meaning. It is a vibrant, self-observing system. The definite world we see emerges not from a single, privileged act of human observation, but from the ceaseless, low-level observation happening in every corner of existence at every moment in time. In this view, the famous double-slit experiment doesn't require a human to collapse the electron's wave function. The very act of the electron interacting with the environment, with other particles that all possess their own proto-consciousness, is sufficient to decohere its state and bring about a definite outcome. We, as human observers, are simply particularly complex and integrated manifestations of this universal substrate of awareness, capable of reflecting upon the process in a way that a single electron cannot. This perspective transforms our understanding of our own place in the cosmos. It suggests a profound kinship with all of existence. The awe you feel when looking at the starry night sky is not just you, a separate entity, observing an external, separate universe. It is the universe, in one of its most complex and integrated forms, observing itself in another of its magnificent forms. The consciousness that allows you to wonder and feel is the same fundamental property that hums within the heart of every star, every planet, and every particle of dust. This is not a mystical retreat from science, but a potential expansion of our scientific worldview, an attempt to include the most undeniable fact of our existence, our own inner experience, into our fundamental description of nature. Panpsychism doesn't provide all the answers. The challenge of how micro-experiences combine into macro-consciousness, known as the combination problem, is a serious and active area of debate. But it reframes the entire conversation, offering a vision of a cosmos that is inherently sentient, a unified, self-experiencing whole in which we are not alien observers, but native participants, intimately connected to the very mind of the universe itself. Perhaps the most direct and startling demonstration of an observer's power over the quantum world comes from a phenomenon known as the quantum Zeno effect, named after the ancient Greek philosopher Zeno of Elea, who proposed a series of paradoxes arguing that motion is an illusion. Zeno famously suggested that an arrow in flight must at any single instant be motionless in a specific point in space. If you take all these motionless instants together, he argued, how can the arrow ever truly move? While classical physics easily resolves this puzzle, the quantum world takes Zeno's idea and makes it eerily real. The quantum Zeno effect reveals that if you observe an unstable quantum system repeatedly and rapidly, you can effectively freeze it in its initial state, preventing it from evolving or decaying. It's as if the constant gaze of a conscious observer acts like a cosmic pause button, holding reality in place through the sheer force of attention. To grasp how this works, let's build on our understanding of the quantum state. Recall that a quantum system, like an atom poised to decay or a particle ready to spin in a new direction, doesn't jump instantly from one state to another. Instead, it evolves smoothly over time, its wave function gradually shifting from describing a high probability of being in the initial state to a high probability of being in a new, final state. This evolution is not a sure thing, it's a drift of probability. Now, imagine this process is like a shy photographer developing a picture in a darkroom. The image slowly begins to appear on the paper. If you were to flash a bright light on the paper at the very first moment, you would see only the faintest ghost of an image, and the developing process would be reset, forcing it to start over from the beginning. If you keep flashing the light over and over again in quick succession, the photograph never gets a chance to develop properly. It remains trapped in its initial undeveloped state. This is precisely what happens in the quantum Zeno effect. Each measurement, each observation acts like that flash of light. It forces the system to show its hand, to collapse back into a definite state. If these collapses happen fast enough, the system simply doesn't have the time to transition into anything else. It is perpetually reset to its starting point, frozen by the relentless pace of observation. A more everyday, if whimsical, analogy can make this wonderfully clear. Think about trying to boil a pot of water on the stove, but with a peculiar rule. You are compelled to constantly lift the lid to check if the water is boiling. Every single time you lift the lid, you let out a burst of steam and heat, slightly cooling the water and interrupting the steady buildup of thermal energy needed for a rolling boil. If you check often enough, say, every half second, the water will never gather the continuous, uninterrupted energy required to reach 100 degrees Celsius. Your obsessive observation actively prevents the event you are looking for from ever happening. In the quantum realm, the boiling is the natural evolution of the system, and your checking is the act of measurement. The constant intervention pins the system in place, demonstrating that observation is not a passive window into reality, but an active force that can dictate the very behavior of the physical world. This isn't just a theoretical curiosity, it has been confirmed in laboratories with stunning precision. In one classic experiment, scientists work with atoms that have been excited to a higher energy level. Left to its own devices, such an atom will spontaneously decay, dropping to a lower energy state and emitting a photon of light. This decay is a random quantum process, but it has a predictable average timescale. However, when researchers continually measure the atom to see if it is still in its excited state, they can dramatically slow down its decay rate. By bombarding the atom with measurements, they effectively keep asking it, "Are you still excited?" And each time the atom is forced to answer yes, its internal quantum clock is reset. The wave function, which was just beginning to evolve toward decay, is collapsed back to the excited state. With measurements coming in a rapid-fire sequence, the atom is never given a quiet moment to make the leap. Its natural instability is suppressed by the watchful eye of the experimenter. The implications of this effect ripple out far beyond a single atom in a lab. It suggests that observers possess a form of gentle control over the quantum world, not through physical force, but through the strategic application of attention. This lends a powerful new dimension to the idea that we are co-creators of reality. It's not merely that we crystallize a single outcome from a fog of possibilities. Our sustained observation can actively maintain a specific reality, holding it steady against its natural tendency to change and evolve. This provides a fascinating potential bridge between the microscopic quantum world and the stability of our macroscopic experience. Could it be that the apparent solidity and persistence of the objects around us is somehow sustained by a continuous, low-level form of observation, perhaps from the environment or even from our own peripheral awareness? While that remains a speculative leap, the quantum Zeno effect stands as one of the most unequivocal demonstrations that in the quantum realm, to watch is not just to see, but to hold, to shape, and to preserve. This brings us to a pivotal and deeply modern question that stands at the frontier of our exploration. We've journeyed through the role of the human observer, but in today's world, we are increasingly surrounded by artificial intelligences and automated systems that can perform complex measurements entirely on their own. This forces us to confront a critical distinction. Does the observer that collapses the quantum wave function need to be a conscious, living being, or is a sophisticated machine simply recording data sufficient to do the job? The answer to this question has the power to either dethrone human consciousness from its special status or to reaffirm it in a startling new way. Let's set up a clear scenario to explore this. Imagine a fully automated version of the double-slit experiment running in a sealed, empty laboratory. A robotic arm loads the electron gun. The electrons are fired one by one at the barrier, and a sophisticated digital detector records where each electron lands on the screen. The entire process is controlled by a computer, and all the data is saved to a hard drive. No human is present. The lab is dark and silent. Now, after the experiment runs for an hour, a scientist arrives, opens the door, and boots up the computer to check the results. The crucial question is, what does the scientist see on the screen? Did the electrons produce an interference pattern, indicating they were behaving as waves throughout the experiment because no one was consciously watching? Or did they produce two simple bands showing they behaved as particles, implying that the automated detector itself caused the wave function to collapse the moment it registered each electron's arrival? From one perspective, the answer seems straightforward. If we define an observation as any interaction that creates an irreversible record of an event, a permanent mark in the universe, then the machine certainly qualifies. The clicking of a Geiger counter, the imprint on a photographic plate, or the bits flipped in a digital memory all represent a point of no return. Information about the quantum system has been copied into the macroscopic environment, and this process of decoherence quickly destroys the delicate superposition. In this view, the conscious awareness of a human is irrelevant. The universe doesn't care who or what reads the record. The simple act of creating the record is what solidifies reality. The automated detector, by its very operation, is constantly asking the quantum system to make a choice, and the system obliges. When the scientist finally arrives, they are merely reading a history that was already written and fixed by the machine's interactions. This interpretation powerfully strengthens the idea that reality is defined by the flow of information itself, a cosmic computation where any irreversible information exchange marks the transition from possibility to fact. However, there is another, more subtle way to look at this. We could argue that while the machine creates a potential for a definite reality, that reality isn't truly finalized until the information enters a conscious mind. In this view, the data on the hard drive exists in a kind of suspended animation. It's like a book sitting on a shelf in a library that no one has ever read. The words are printed on the page, but the story they tell hasn't truly entered the world of conscious experience. Until the scientist opens the file and becomes consciously aware of the result, the entire chain of events, the electrons, the detector, the hard drive, could still be considered part of a giant, entangled quantum system. The wave function describing this entire setup would include the superposition of the hard drive having recorded an interference pattern and the hard drive having recorded two particle bands. It's only when the scientist looks at the screen that this massive superposition collapses and they see one specific, consistent history. In this scenario, the conscious observer is not just another physical system. They are the ultimate arbiter that selects a single, shared timeline from a haze of potential past. This debate isn't merely philosophical, it has been probed in laboratories. Researchers have designed experiments where a quantum system is measured by a device, and the result is stored in a quantum memory, a memory that itself can be in a superposition. They can then choose to either erase that memory without ever looking at the data or to finally observe it. Astonishingly, when the information is coherently erased, it's as if the measurement never happened. The quantum system can be shown to have retained its wave-like behavior. This suggests that it's not the physical disturbance of the detector that matters most, but the irreversible creation of information that is in principle accessible to a conscious being. A machine that records data and then immediately, permanently destroys it before any consciousness can access it might not count as a true observation. But a machine that creates a permanent, readable record seems to finalize the event regardless of when, or even if, a human ever looks at it. So, what are the profound implications of this? If we accept that a machine can cause wave function collapse, it significantly weakens the direct, special link between human consciousness and the creation of reality. It suggests that the universe operates on a set of physical rules that are objective and automatic, and that the emergence of definite facts is a consequence of information becoming embedded in the environment through decoherence. We are not magical collapse triggers, but simply complex products of this same decoherent world. This is a more humble, if also a more physically grounded, view of our place in the cosmos. The grandeur of the participatory universe shifts from our minds to the impersonal processing of information. Reality becomes a self-recording system, and we are just one type of system that has evolved to read those records. Yet, even this humbler view carries a breathtaking consequence. It strengthens the radical idea that reality is, at its heart, informational. The transition from the fuzzy quantum realm to the definite classical world isn't marked by a mystical act of conscious will, but by the practical, physical process of information amplification. When a single electron's position is recorded by a detector, that one bit of information is copied into trillions of atoms in the device, then into the storage medium, and so on. This irreversible copying is what makes the event real and classical. In this light, the universe begins to look less like a collection of solid objects and more like a vast, dynamic network of information being constantly processed and shared. The question, what is real, transforms into what information has been irreversibly stored. This perspective, championed by figures like John Wheeler with his It from Bit, suggests that the bedrock of existence is not material but computational. The particles and forces we measure are the output of this cosmic computation, and every measurement, whether by machine or mind, is a step in the universe's ongoing process of defining itself. This exploration of machines as observers inevitably leads us to a more fundamental and perhaps even stranger question, one that takes us from the sterile environment of the laboratory out into the vibrant, living world. If we are seriously considering whether a silicon-based computer can collapse a wave function, then we must also ask, what about the vast kingdom of life itself? Could the act of observation, this profound creative force, be a capacity shared not just by humans, but by all biological entities, from the simplest bacterium to the family dog, and even to the tree outside your window? This idea pushes the boundary of the observer effect into the realm of biology, forcing us to consider different levels of consciousness and interaction with the world. Let's start with what might seem like the most distant case, the plant kingdom. At first glance, the idea that a rose bush or an oak tree could be a quantum observer seems far-fetched. Plants don't have a central nervous system, let alone a brain that can contemplate the results of an experiment. However, if we define an observation in the most physical, quantum informational sense as an interaction that extracts information from a system and records it in a way that leads to decoherence, then the picture becomes much more intriguing. Consider the process of photosynthesis, the miraculous engine of life on Earth. A plant's leaf is a sophisticated solar panel designed to capture photons of light and convert their energy into chemical fuel. For decades, biologists assumed this was a straightforward, if complex, classical process. But startling research over the past years has revealed something extraordinary. The initial stages of photosynthesis appear to involve quantum coherence. Inside the light-harvesting complexes of a plant's cells, the energy from an absorbed photon doesn't just bump along a chain of molecules like a pinball. Instead, it seems to explore multiple pathways simultaneously, using a quantum search strategy to find the most efficient route to the reaction center where it can be used. This is a bona fide quantum phenomenon happening in a warm, wet, living system. Now, at the end of this process, the energy is converted and stored. The plant has, in a very real sense, taken a quantum system, the incoming light, and through its biological machinery, forced it into a definite classical outcome, stored chemical energy. Has the plant measured the photon? From a purely physical perspective, its cellular machinery has certainly interacted with the quantum system, extracted information, the photon's energy, and irreversibly recorded that information in its molecular structure. While it's a massive leap to ascribe conscious awareness to the plant, its very biological function relies on a process that captures and defines a quantum event, blurring the line between a passive receptor and an active participant in shaping reality. Moving up the ladder of biological complexity, we encounter animals with nervous systems, creatures like the domestic cat. This brings us right back to Schrödinger's famous thought experiment, but now we're asking a different question. It's not about whether the cat is in a superposition, but whether the cat itself could be the observer that collapses superpositions within its own environment. A cat possesses a sophisticated brain, sensory organs, and a clear capacity for conscious experience. It feels hunger, curiosity, and affection. When a cat stalks a mouse, its eyes are gathering photons, its ears are capturing sound waves, and its brain is integrating this sensory data to form a coherent model of its world. Each of those sensory interactions is at its core a quantum measurement. The rod and cone cells in the cat's retina are absorbing individual photons, an event that collapses their wave function and sends a definite signal to the brain. From this perspective, the cat is unquestionably a continuous, living observer, constantly collapsing the quantum fuzziness in its immediate surroundings into a definite, classical reality that it can navigate and interact with. Its consciousness, while different from our own, is a real and potent force for localizing reality. The world as perceived by the cat is solid and definite because the cat's own sensory apparatus is making it so. This suggests that the privilege of being an observer is not a uniquely human trait, but a property of any sufficiently complex conscious being that interacts with its environment through measurement-like processes. The universe a cat experiences is just as real and just as classical as the one we do, because the cat is actively co-creating it through the very act of perception. This biological spectrum, from photosynthesizing plants to conscious cats, presents us with a profound and difficult-to-answer question. Where exactly do we draw the line? Is there a specific threshold of neural complexity that must be crossed before an entity graduates from merely processing environmental data to truly observing in the quantum sense? Perhaps the key isn't the presence of a brain, but the capacity for an integrated, subjective experience, what philosophers call phenomenal consciousness. A bacterium, for instance, can sense and move toward a food gradient. It is processing information about its environment and responding, but does it feel like anything to be a bacterium? Does it have a point of view? Most would argue probably not. It's a sophisticated biological automaton. A cat, on the other hand, almost certainly has a rich inner world of sensations and feelings. The plant sits in a much grayer area. It responds to light, gravity, and touch in remarkably complex ways, but the absence of a central nervous system makes the existence of any unified subjective experience highly unlikely. This ambiguity forces us to confront the two primary interpretations of the observer's role that we've discussed. If we take the view that wave function collapse is caused by any irreversible information transfer, the decoherence view, then the line is very blurry indeed. A plant, a cat, and a digital camera all qualify as observers because they all physically interact with quantum systems and record the outcome in some stable form. The universe in this picture becomes classical through a near infinite number of such interactions happening everywhere all the time. Life is just a particularly intricate form of this universal process. However, if we lean toward the more radical view that true collapse requires a conscious, subjective awareness, the von Neumann/Wigner perspective, then the line becomes much sharper and also much more mysterious. In this view, only entities that possess genuine consciousness can finalize reality. The cat qualifies, the plant and the bacterium do not. This creates a fascinating, layered reality. The quantum world remains a soup of potentiality at the microscopic level, only snapping into concrete existence when it intersects with a conscious mind. This would mean that the world perceived by a conscious animal is fundamentally more real, or at least more definitively actualized, than the world as it exists in the absence of such awareness. Ultimately, this journey through the biological world doesn't give us a final, easy answer, but it profoundly deepens the mystery. It suggests that the act of observation might not be a single, well-defined phenomenon, but a spectrum that mirrors the spectrum of life itself. From the mindless, information-gathering processes of a leaf to the vivid, feeling-rich awareness of an animal, biology presents us with a continuum of interaction with the quantum world. This blurs the distinction between the living and the non-living, the conscious and the unconscious, suggesting that the universe's transition from possibility to reality is a collaborative project, a dance involving countless participants at every level of complexity. We are not the sole authors of reality, but perhaps the most articulate narrators in a cosmos teeming with silent partners, all of us in our own ways, engaged in the continuous, creative act of bringing the universe into focus. But what if the very stage upon which this quantum drama unfolds the dimension of time itself isn't quite what it seems? To explore this, we need to step away from the subatomic world and into the cosmic arena, guided by the towering genius of Albert Einstein. His theories of relativity didn't just give us E equals mc squared. They shattered our everyday understanding of time, replacing the flowing river of moments with a startlingly different structure known as the block universe. In this four-dimensional picture, the entire history of the cosmos, everything that ever was, is, or will be exists all at once, laid out like a finished film on a celestial reel. This timeless perspective, often called eternalism, forces us to confront a profound question. If the past and future are just as real as the present, what happens to the power of the observer, an act that seems to depend so crucially on a unique and fleeting now? Let's unpack this strange but powerful idea. In our daily lives, we experience time as a relentless, one-way flow. The past is gone, a collection of memories. The future is a realm of anticipation and uncertainty. And the present is a razor-thin edge, a single moment of now that we feel we are moving through. This experience is so intuitive that we rarely question it. But Einstein's special relativity tells a completely different story. He revealed that there is no universal, tick-tocking clock for the entire cosmos. Instead, time is relative. It stretches and compresses depending on your speed and the strength of the gravity you're experiencing. More profoundly, he showed that space and time are not separate entities but are woven together into a single, four-dimensional fabric called space-time. In this fabric, every event, your birth, the fall of a star, the making of this video, has a set of space-time coordinates, a fixed location in the cosmic grid. From this God's eye view, the universe isn't becoming, it simply is. The entire expanse of history is a single, static, four-dimensional block. Your childhood, your life at this very second, and every moment of your future are all equally real and permanently etched into the structure of reality, just as the cities of Paris, Tokyo, and New York all permanently exist at different locations in space. This concept of a block universe presents a radical challenge to the quantum ideas we've been exploring. The entire quantum mystery revolves around the act of observation happening in a present moment that seems to change the future. A wave function collapses now, creating a definite reality from that point forward. But if the block universe is correct, the future is not open to being changed. It's already out there, fully formed. This forces a difficult reconciliation. How can an observer's free choice to measure a particle in a certain way have any creative power if the outcome of that measurement is already a fixed part of the four-dimensional block? It suggests a deeply deterministic cosmos where the apparent randomness of quantum events is just an illusion born from our limited, single-moment perspective. From outside of time, every single quantum measurement, every collapse, and every observer's conscious experience of that result is pre-written into the eternal fabric of space-time. The electron in the double-slit experiment was always going to be measured in a specific spot at a specific time. The cat in Schrödinger's box was always either alive or dead from the very beginning of the universe. There was no superposition waiting to be resolved, only a single, unchangeable timeline. This deterministic picture, flowing from Einstein's work, stands in stark contrast to the seemingly active, creative role of the observer in quantum mechanics. Einstein himself was deeply troubled by the probabilistic nature of quantum theory, famously quipping that God does not play dice with the universe. He believed in a reality that was objective and independent of measurement, a view that aligns much more comfortably with the block universe. In his cosmos, there are no ghostly superpositions, there is only the single, solid block. The observer isn't a creator, but a traveler moving along a pre-laid track, illuminating with their consciousness a single, thin slice of the block at a time, which they experience as the present. The feeling of making a choice, of causing a collapse, is just that, a feeling. The choice and its outcome were always part of the grand, unchanging structure. So where does this leave our grand question of whether observers create the universe? The block universe offers a humbling counterpoint. It suggests that the universe doesn't need to be created moment by moment because the entire creation is already a finished work. We are not the architects of reality, but the audience experiencing a cosmic play whose script is complete. Our journey of observation is not one of building the set, but of simply reading the lines that have already been written for us, discovering a story that was always there. This doesn't make our experience any less real or meaningful, but it does relocate our role from active participants to conscious witnesses to a magnificently preordained existence. The block universe and the quantum observer present us with two powerful, competing visions of reality. One, a dynamic, participatory process unfolding in a flowing present, and the other, a majestic, static tapestry where all of time exists at once. Our current understanding of physics cannot yet tell us which of these breathtaking pictures is the true one, leaving us suspended between a universe that we actively shape and a universe that has already shaped us, forever caught between the thrill of possibility and the comfort of a timeless, eternal destiny. All of these mind-bending theories and thought experiments would remain in the realm of pure philosophy, if not for the relentless work of experimental physicists who have dedicated themselves to designing and building machines that can force the quantum world to answer our most probing questions. Over the past few decades, laboratories around the globe have transformed from passive observation posts into active testing grounds for the very nature of reality, pushing quantum weirdness into larger and larger systems to see where and if it finally breaks. One of the most fertile grounds for this exploration has been the field of quantum optics, where scientists manipulate individual particles of light with breathtaking precision. Modern versions of the double-slit experiment have become incredibly sophisticated, using photons that are individually released and tracked. In one stunning variation, known as the quantum eraser experiment, physicists demonstrate that they can seemingly change the past behavior of a photon after it has already been detected. They can set up an apparatus that allows them to decide, well after the photon has passed through the slits and hit the screen, whether to obtain which path information, which would show it behaved as a particle, or to erase that information, which miraculously restores the wave-like interference pattern. This doesn't literally change the past, but it powerfully illustrates that no single history is definitive until the entire measurement context, the full question we choose to ask, is finally settled. It suggests that the universe doesn't commit to a specific storyline until the very last possible moment, keeping all options open in a state of quantum potential. Moving beyond light, researchers have turned to the world of superconductivity to build the essential tools of this new quantum age, qubits. These are tiny circuits, often cooled to temperatures colder than deep space, where electricity can flow without resistance. In this exotic environment, the circuit doesn't just have a defined state of current flowing one way or the other. It can be placed in a precise superposition of both states simultaneously. These superconducting qubits are the building blocks of quantum computers, but they are also perfect laboratories for studying the measurement problem itself. Scientists can delicately couple a qubit to a measurement device and then control the strength of the interaction. They can watch in real time as the qubit's fragile superposition is slowly destroyed by its environment, a process decoherence makes visible. In some experiments, they use what's called a weak measurement, which extracts just a tiny bit of information from the system, causing only a partial collapse. This allows them to almost catch the quantum state in the act of deciding, observing its gradual transition from a fuzzy mix of possibilities into a single classical fact. These experiments are charting the murky boundary where the quantum world gives way to the classical, not with a single mysterious bang, but through a continuous and measurable process of interaction. Perhaps the most direct assault on the question of scale has come from the field of massive molecule interferometry. For many years, the quintessential quantum weirdness of superposition and interference was the exclusive domain of the very small, electrons, photons, and individual atoms. The central, unanswered question was always, how big can an object be and still exhibit these bizarre properties? To find out, physicists have been designing monumental machines, some stories tall, to perform interference experiments with increasingly large molecules. The journey began with simple molecules like Buckminster fullerene, soccer ball-shaped cages of 60 carbon atoms. Despite being large enough to be seen with powerful microscopes, these molecules, when fired through a grating, produced a clear interference pattern. They were behaving as waves. The experiments didn't stop there. Researchers have now successfully demonstrated quantum interference with molecules composed of thousands of atoms, pushing the mass limit further and further. Each successful experiment is a profound demonstration that there is no fundamental size limit written into the laws of quantum mechanics. An object doesn't suddenly stop obeying quantum rules because it becomes too big. It stops because it becomes increasingly difficult to isolate it from the environment. These massive molecules are so complex that they are constantly on the verge of interacting with a stray air molecule or emitting a photon of heat, which would instantly destroy their delicate quantum state. By achieving these feats in ultra-high vacuums and at cryogenic temperatures, scientists are proving that quantum behavior isn't a quirk of the small, but a fundamental property of all matter, one that is simply drowned out by noise in our warm, messy, everyday world. The ultimate goal of many of these modern experiments is to isolate the very moment of wave-function collapse and determine its trigger. This is the holy grail of quantum foundations, an attempt to move from describing what happens during a measurement to explaining why it happens. One groundbreaking approach involves creating what are called cat states, not with felines but with microscopic systems that are put into a superposition of two distinctly different states, like a tiny drumhead vibrating and not vibrating at the same time. By coupling these miniature cat states to a sensitive measuring apparatus, physicists hope to witness the transition itself. The question they are trying to answer is stark. Does the collapse occur smoothly and continuously as decoherence theory suggests, with the environment gradually washing away the quantum effects? Or is it a sudden, discontinuous jump, a genuine collapse as envisioned in the original Copenhagen interpretation? Early evidence from monitoring qubits suggests that the collapse, when it happens, is indeed abrupt, a quantum jump. But these jumps are not entirely random. There are subtle precursors, fleeting signals that a jump is about to occur, hinting that even this most mysterious of processes may have underlying dynamics we can someday understand. All of this tangible data is forcing the philosophical debate out of the ivory tower and into the laser-lit halls of the laboratory. The line between metaphysics and physics is blurring. When a team in Vienna manages to put a molecule containing over 2,000 atoms into a quantum superposition, they are not just performing a technical stunt, they are conducting a direct test of the limits of reality itself. They are asking the cosmos point blank if a tiny piece of the classical world can be made to behave in a quantum way, challenging the very definition of what it means to be an object. Similarly, experiments that aim to put a small but visible mirror into a superposition of two positions are probing the connection between quantum mechanics and gravity, a frontier that might hold the key to unifying all of physics. Each new result, each pushed boundary, adds a new data point to the grand puzzle. We are no longer just wondering about a cat in a box. We are building boxes for progressively larger and more complex systems, carefully opening the lid with ever more sensitive instruments and watching with bated breath to see what is inside. The answer is no longer a matter of interpretation alone. It is becoming a matter of empirical fact, a reading on a dial, a pattern on a screen, bringing us closer than ever to understanding the profound role we play in the universe we perceive. But as we stand amidst these grand theories and experimental wonders, we find ourselves circling back to what might be the most stubborn and profound mystery of all, not in the cosmos but within ourselves. This is the challenge of consciousness, often called the hard problem, a term coined by philosopher David Chalmers to distinguish it from what he calls the easy problems. Now, don't be fooled by that name. The easy problems are still incredibly complex. They involve figuring out how the brain integrates information, focuses attention, or controls behavior, tasks that, while monumentally difficult, are ultimately problems of mechanism. We can imagine building a sophisticated robot or a complex computer program that could, in principle, perform these functions. We could trace the neural pathways, map the algorithms, and explain how the system works in purely physical terms. The hard problem, however, is of an entirely different nature. It asks a simple question with no simple answer. Why and how do all these intricate physical processes, the firing of neurons, the exchange of neurotransmitters, give rise to the inner, subjective world of experience? Why is there something it is like to be you? This is the mystery of qualia, the raw feels of existence, the piercing redness of a sunset, the aching sweetness of a memory, the dull throb of a headache. These are not just data points processed by a biological computer. They are the very fabric of our reality, and we have no scientific explanation for why they should exist at all. To grasp the depth of this chasm, consider the difference between describing a symphony and actually hearing it. A neuroscientist could give you a perfect moment-by-moment account of the auditory processing in your brain as you listen to Beethoven's Fifth. They could show you the precise frequencies being decoded, the regions of the brain lighting up with activity, and the motor responses priming your body for the music's emotional impact. This is a description of the orchestra's instruments, the sheet music, and the physical vibrations in the air. But this entire objective account leaves out the most important part, the soaring, triumphant feeling the music evokes within you. That subjective, first-person experience, the qualia of the symphony, is what the hard problem is all about. We can describe the physical correlates of consciousness until the end of time, but that description will always contain a gap, an unbridged leap from the objective description of a process to the subjective reality of an experience. This is the infamous explanatory gap. We can explain what the brain does, but we cannot explain how or why doing those things generates an inner universe of sight, sound, and sensation. This gap becomes critically important when we try to link consciousness to its potential role in quantum mechanics. If we want to claim that a conscious observer is what collapses the wave function, we immediately run into a monumental challenge. We have no coherent scientific definition of what consciousness is. Is it a substance, a process, an emergent property? We don't know. Proponents of views like von Neumann's, which place consciousness at the end of the measurement chain, are essentially inserting a mystery into the heart of physics to solve another mystery. It's like having a perfectly good mathematical equation and then, at the very last step, replacing a variable with a question mark. We are saying that an undefined X-consciousness is the fundamental agent that finalizes reality. This doesn't so much solve the measurement problem as it relabels it, moving the mystery from the quantum realm into the realm of the mind. Without a physical theory of consciousness, the idea that it causes collapse remains a fascinating but ultimately speculative proposition, a philosophical placeholder for a mechanism we cannot yet describe. This ambiguity creates a cascade of difficult questions. If consciousness is the collapse trigger, what level of consciousness is required? Does it demand the rich self-awareness of an adult human? Would a chimpanzee suffice? What about a mouse or a fish or a worm with a rudimentary nervous system? If we follow this logic all the way down, we are forced to consider a kind of panpsychist view, where even the simplest particles possess some form of proto-consciousness. But this, too, simply pushes the explanatory gap down to a more fundamental level. It swaps the problem of how consciousness emerges from matter for the problem of how micro-consciousness combines into macro-consciousness, a challenge known as the combination problem. We are still left with a gap, just a smaller and more numerous one. Alternatively, if we try to use decoherence to explain the emergence of the classical world without consciousness, we seem to have solved the physics problem, but we are still left with the hard problem untouched. We can explain why the world appears definite to us, but we cannot explain why there is a us having an appearance in the first place. The two mysteries, the quantum measurement problem and the hard problem of consciousness, run on parallel tracks, and we have not yet found the junction where they meet. Ultimately, this philosophical grounding serves as a crucial reality check, a reminder of the profound unknowns that still lie at the foundation of our quest. The tantalizing possibility that we are co-creators of the universe rests on a premise we cannot yet substantiate. It's like trying to build a skyscraper without fully understanding the properties of steel. We can see the grand design, we can admire the blueprint, but we cannot be sure the central supporting structure will hold. This isn't a reason to abandon the search. It is a call for humility and for a broader, more interdisciplinary effort. To truly understand the observer's role, we may need nothing less than a revolution that unifies physics with a true science of consciousness, bridging the explanatory gap and finally telling us what this subjective experience, this light of awareness, actually is. Until that day comes, the ultimate power of the observer remains one of the most compelling and unresolved puzzles in all of human thought. a beacon drawing us toward a deeper understanding of both the cosmos and our own mind. Now we arrive at a question that cuts to the very core of our human experience. If the act of observation plays such a fundamental role in shaping reality, what does that mean for our own freedom to choose? For centuries, philosophers have grappled with the puzzle of free will, the sense that we are the authors of our own actions versus determinism, the idea that every event is the inevitable result of prior causes. Our intuitive feeling is that we make genuine choices, that you freely decided to watch this video, that you can choose to pause it, that your future is a landscape of open possibilities shaped by your decisions. But the strange rules of quantum mechanics and their various interpretations cast this familiar notion in a startling new light, forcing us to reconsider the very nature of human agency. If we embrace the original Copenhagen interpretation, where a conscious observer collapses probabilities into a single reality, it seems to grant us a form of breathtaking creative power. Every time we direct our attention, every time we ask a question of the universe, we are not just passive receivers of information. We are active participants in a cosmic selection process, choosing one timeline from a vast menu of potentialities. This perspective feels intensely empowering. It suggests that our focused intention and awareness are not epiphenomena, but genuine forces that sculpt the world around us. Your life's path, in this view, isn't a pre-written script. It is a collaborative creation between the inherent probabilities of the cosmos and the specific observations you choose to make. Your decisions matter in the most profound way possible. They are the very mechanism that carves a definitive reality out of the quantum fog. This imbues our lives with immense significance and responsibility. It means that the future is genuinely open, waiting for our conscious gaze to give it form. Yet, this empowering vision comes with a daunting, almost paradoxical flip side. While our observation may select a reality, do we truly have free will over what we observe and how we collapse the wave function? The process of collapse, as described in the Standard Model, is random. When you measure an electron's spin, the outcome is not determined by your desires or your will. It is governed by probability. You might want it to be spin up, but the quantum dice may land on spin down. So, if the collapse itself is random, where is our freedom? It seems we have the power to ask the question, but not to control the answer. Our creative agency is then limited to deciding where to point the spotlight of our consciousness, while the specific scene that is illuminated is a matter of chance. This creates a strange hybrid model of free will. We are free to explore and interact, but the specific outcomes we encounter have an element of fundamental randomness woven into their fabric. Our life's journey becomes a series of choices about which questions to ask, followed by a random answer from the universe, which then presents us with a new set of questions. This isn't the classic, all-powerful free will we might imagine, but it is a far cry from a clockwork universe where everything is predetermined from the Big Bang. Now, let's turn this entire concept on its head by considering the many worlds interpretation. In this breathtaking vision, the wave function never collapses. There is no single random selection. Instead, every single possible outcome of every quantum event actually happens in its own separate, equally real branch of reality. The implications for free will are nothing short of staggering. In the many worlds universe, you do not choose one path. You take all paths. At this very moment, there is a version of you who decided to keep watching this video, and another version who clicked away to watch something about cat videos. There's a version who paused to get a snack, and a version who is taking meticulous notes. Every possible decision you could ever make is realized in some branch of the multiverse. From this God's eye view, the concept of free will as we understand it begins to evaporate. If every alternative is actualized, then you are never truly making a choice between possibilities. You are simply traveling along one thread in an infinite tapestry where all patterns are simultaneously woven. The feeling of making a decision is just your conscious awareness tracking along a single, predetermined branch. Your life story isn't one you are writing, it is one you are reading, while an infinite number of other yous are reading every other possible version of the story. This is the ultimate deterministic nightmare disguised as infinite possibility. It suggests that our deep-seated intuition of free will is a magnificent illusion, a necessary artifact of being trapped in a single stream of consciousness within an ocean of parallel realities. This collision between physics and philosophy forces us to confront the very meaning of personal responsibility. If the Copenhagen interpretation is correct and our observations do indeed collapse reality, then our intentions and our focus matter profoundly. We are, in a very real sense, responsible for the world we help to create. This could be seen as a scientific foundation for mindfulness and intentional living, the idea that where we place our attention actively shapes our reality, and thus we must choose wisely. Conversely, if the many worlds interpretation is true and all choices are made, the notion of moral responsibility becomes vastly more complex. Is a version of you who commits a terrible act in one branch any more or less you than the version in another branch who performs a great act of charity? If all potentialities are realized, then blame and praise seem to lose their absolute meaning, becoming merely local judgments within a specific branch. Our entire legal and ethical systems are built on the assumption that individuals could have done otherwise, but in a many worlds reality, they both did and did not do otherwise in different worlds. Ultimately, these scientific interpretations do not provide easy answers to the ancient riddle of free will. Instead, they reframe the debate in a dazzling new context. They present us with two profoundly different visions of our place in the cosmos. In one, we are active, conscious sculptors of a single, unfolding reality, imbued with a creative power that is both awesome and humbling. In the other, we are eternal travelers on an infinite number of pre-laid tracks, experiencing the poignant and convincing illusion of choice. Both visions are consistent with the mathematics of quantum theory, and both challenge our most basic assumptions about who we are. Perhaps the final lesson is that the universe is far stranger and more wondrous than our classical intuitions can grasp, and that the mystery of our own agency is inextricably linked to the deepest, unsolved mysteries of reality itself. Let's take this one step further and connect the observer's role to a truly mind-bending modern idea, the simulation hypothesis. This is the notion that our universe, with all its galaxies, life, and consciousness, may not be the ultimate base reality, but rather an incredibly advanced digital construct, something like a hyper-realistic video game running on a computer of unimaginable power. If that were true, it would provide a powerful and surprisingly intuitive technological metaphor for understanding the quantum observer. In a simulation, what we call observation might simply be the process of the central processing unit rendering data for a user or a specific subroutine. Think about a modern open-world video game. The entire digital landscape isn't rendered in perfect detail all at once. That would be computationally wasteful and incredibly slow. Instead, the game engine uses a technique called level of detail or frustum culling. Only the parts of the world that a player is actually looking at are rendered in high resolution. The forest behind you, the buildings on the other side of the city, they exist as low-resolution models or simple data points in the code until you turn your character to face them. At that moment, the computer dedicates resources to draw them fully into your field of view. In a very similar way, the bizarre quantum phenomenon of superposition, where a particle exists in multiple states at once until measured, could be seen as the universe's source code operating in a resource-optimized mode. The electron isn't in a definite place because the simulation hasn't bothered to calculate a specific position for it until a conscious observer, or a measuring device that feeds data to an observer, forces the system to resolve that value. The wave function is the raw, unrendered data, and the act of observation is the command that tells the cosmic computer, "Process this now, I need to see the result." This perspective elegantly reframes some of the most puzzling quantum behaviors. The random nature of wave function collapse is no longer a mysterious property of reality, but simply a feature of the algorithm. When you ask the simulation for a definite value, it runs a random number generator based on the probability distribution described by the wave function. The outcome isn't predetermined, it's computed on the fly, which is exactly how video games create the illusion of unpredictability. The famous double-slit experiment, where electrons behave as waves when not observed and as particles when watched, fits perfectly into this model. When no one is checking which slit the electron goes through, the simulation doesn't need to assign it a specific path. It can treat it as a spread-out wave of probability, which is computationally much cheaper. But the instant a detector is placed to observe the path, the simulation must now generate a specific, consistent history for that electron, forcing it to pick a single slit and behave like a localized particle. It's as if the program has received a request for high-fidelity data and must now allocate the processing power to deliver it. Even the spooky phenomenon of quantum entanglement, where two particles remain connected across vast distances, could be explained as a clever programming trick. Instead of independently calculating the state of each particle, which would require constant communication faster than light, the simulation could simply tag them as a linked pair. When the state of one is measured, the code instantly updates the state of the other, maintaining consistency within the rendered reality for any local observer. This isn't magic, it's efficient database management. The simulation hypothesis also offers a fresh take on the different interpretations of quantum mechanics. The Copenhagen interpretation, with its mysterious collapse, aligns with the idea of a simulation rendering events upon observation. The many worlds interpretation, where every possibility branches into a new universe, could be seen as a different computational strategy, one where the simulation doesn't bother with collapse at all, but instead calculates every possible branch in parallel, conserving its total processing power by not having to constantly resolve ambiguities. In this view, we don't experience the other branches not because they aren't real, but because our conscious awareness is locked to a single thread of execution within the vast multitasking processor. The concept of quantum decoherence, which explains how interactions with the environment destroy quantum effects, finds a natural analogy in data propagation. Once a quantum event is measured, that information doesn't just vanish. It gets copied into trillions of atoms in the environment, like a piece of data being written from a computer's fast but volatile cache out to the permanent hard drive. This makes the result classical and irreversible, a fixed part of the simulation's saved history. While it's crucial to remember that the simulation hypothesis is a philosophical proposition and not a proven scientific theory, its value lies in the powerful metaphor it provides. It demystifies the observer effect by giving us a tangible, technological framework to imagine how it might operate. We are no longer grappling with an abstract, metaphysical force, but with a potential set of engineering principles for reality itself. This shifts the role of the conscious observer from a mystical collapse trigger to something akin to a user in a vast virtual reality. Our looking, our questioning, and our measuring are the inputs that prompt the universe to generate outputs, to resolve its equations, and to present us with a stable, consistent world. It suggests that the bedrock of existence may not be matter or energy, but information and computation. Whether our universe is literally a simulation or not, this powerful idea encourages us to see the laws of physics not as rigid commandments, but as the operating system of a cosmos that is interactive, responsive, and fundamentally participatory. What's truly remarkable is that these revolutionary ideas emerging from our most advanced physics labs were, in many ways, anticipated thousands of years ago by the profound contemplative traditions of the East. While Western science was busy building its model of a separate, objective world, the sages and mystics of India and Tibet were diving deep into the nature of mind and reality, arriving at a strikingly similar conclusion. The fundamental separation we perceive between the observer and the observed is a powerful and convincing illusion. In the philosophical system known as Advaita Vedanta, which means non-dualism, this illusion is called Maya. It's a concept often misunderstood as meaning that the world is simply unreal, like a mirage. But a more nuanced understanding reveals that Maya signifies the world's dependent, relative reality. It is real in the way a dream is real while you are in it, but it lacks the independent, substantial existence we normally attribute to it. The central teaching of Advaita Vedanta is that beneath this shimmering display of names and forms, there is only one ultimate, non-dual reality, Brahman, the formless, timeless ground of all being. And here is the most stunning parallel. This tradition teaches that your own deepest self, your Atman, is not a separate, individual soul trapped in a body, but is in fact identical with Brahman. The observer, in its purest essence, is the observed. The seer and the seen are one. This ancient wisdom finds a powerful echo in the Buddhist traditions that arose a few centuries later. The Buddha's core teaching of dependent origination posits that nothing exists independently. All phenomena arise in dependence upon causes and conditions, including the very notion of a separate, permanent self. Buddhism meticulously deconstructs the experience of a solid I that is looking out at a separate world. What we call the self is instead a constantly changing flow of aggregates: form, sensation, perception, mental formations, and consciousness, all interdependent and empty of any isolated existence. The feeling of being a distinct observer standing apart from the universe is, from this perspective, the root of suffering. It creates a subject-object split that leads to craving, aversion, and a sense of alienation. The goal of Buddhist practice is to see through this illusion, to realize a state of non-dual awareness where the boundaries between inner and outer dissolve. In the vivid words of Zen master Dogen, to study the Buddha way is to study the self. To study the self is to forget the self. To forget the self is to be confirmed by all things. This is not a nihilistic annihilation, but an expansive unification, a recognition that the consciousness perceiving the mountain is not looking at the mountain from a distance, but is an intimate, inseparable part of the mountain's own manifestation. When we place these ancient insights alongside the quantum puzzle, the resonance is nothing short of breathtaking. The quantum wave function, with its blur of unresolved potential, mirrors the concept of the unmanifest Brahman, or the luminous, empty ground of being described in Tibetan Buddhism. The act of measurement, which collapses this potential into a specific particle, is eerily similar to the process described in these wisdom traditions where the unmanifest consciousness, through the faculty of attention, gives rise to the manifest world. The physicist's laboratory and the meditator's cushion begin to point toward the same profound truth. Reality is not a pre-existing, external sculpture that we passively observe, but is more like a living, interactive dance that comes into being through the very act of our participation. Just as the Advaita sage declares that Atman and Brahman are one, quantum mechanics, in its own mathematical language, suggests that the observer and the system are an entangled whole, impossible to fully separate. The experimental apparatus and the consciousness of the scientist are not external to the experiment. They are integral parts of the quantum system they are trying to measure. This philosophical confluence offers a powerful new lens through which to view the entire scientific endeavor. The classical scientific method was built on the ideal of a detached, objective observer, a neutral witness who could study the world without altering it. But both quantum physics and Eastern non-duality have shattered that ideal. They reveal that true understanding comes not from maintaining a sterile separation, but from acknowledging our deep, fundamental entanglement with the cosmos we are trying to comprehend. The universe is not a machine we are reverse engineering from the outside. We are the universe awakening to itself from the inside. This doesn't invalidate science, it enriches it, inviting a more humble and participatory relationship with nature. The data from our particle colliders and the revelations from centuries of deep meditation are not contradictory narratives, but different dialects of the same cosmic story. A story that hints we are not lonely spectators in a vast, indifferent universe, but active, conscious participants in a magnificent, unified, and ongoing creation. Now, despite the profound implications we've explored, it's absolutely crucial to recognize that this entire observer-centric view of reality is far from settled science. In fact, many of the most respected minds in physics view these ideas with deep skepticism, arguing that they represent a fundamental misinterpretation of the quantum formalism and veer dangerously close to what's often dismissed as quantum mysticism. To present a truly balanced picture, we must give these powerful criticisms their due weight. Leading this charge was the Nobel laureate Steven Weinberg, a towering figure in theoretical physics. Weinberg expressed a profound unease with granting consciousness any special role in the laws of nature. For him, physics is the study of an objective reality that exists independently of us, governed by mathematical laws that do not require a mind to complete them. He argued that inserting an undefined, non-physical entity like consciousness into the heart of quantum mechanics is not an explanation at all, but a retreat from the scientific mission. It's like having a beautifully engineered car and then claiming it only moves because of a ghost in the engine. Such an idea, he felt, halts progress by appealing to a mystery we cannot test or quantify. Weinberg and like-minded physicists believe the true resolution to the measurement problem will come from a future, more complete theory, one that explains the emergence of a definite world using purely physical principles without any appeal to the human mind. A central pillar of this skeptical view is the powerful argument that the so-called observer effect is being wildly misconstrued in popular discussions. In this more conservative interpretation, an observer doesn't need to be conscious or even alive. It is simply any physical system that becomes entangled with the quantum system in question. When a Geiger counter clicks, it's not the conscious awareness of the scientist that collapses the wave function. It's the irreversible interaction between the radioactive atom and the atoms in the detector. This process, driven by decoherence, rapidly amplifies a quantum event into the classical realm, creating a definite record. From this perspective, the entire universe is constantly observing itself through a near-infinite web of interactions. The moon is definitely in the sky whether a human looks at it or not, because it is perpetually being bombarded by sunlight, cosmic rays, and the gravitational influence of other celestial bodies. These countless interactions continuously decohere the moon's quantum state, pinning it firmly in the classical world. In this view, consciousness is merely a spectator to a physical process that was already long finished. We are not the creators of reality. We are simply complex systems that have evolved to receive and process information about a reality that has already been made definite by its own internal, mindless dynamics. This criticism often crystallizes into a specific charge. That linking consciousness to wave function collapse is a form of promissory anthropocentrism, a comforting but ultimately unscientific desire to place humanity back at the center of the cosmic stage after centuries of scientific discovery have consistently displaced us. We learned the Earth is not the center of the solar system, that the Sun is an average star in a remote corner of a common galaxy, and that we are the product of a blind evolutionary process. The quantum observer hypothesis, critics argue, is a seductive attempt to reclaim a position of cosmic importance. It feels empowering to think that our gaze gives substance to the universe, but this may be more about our psychological needs than an accurate description of physical law. This line of thinking is often labeled quantum mysticism, the blending of genuine quantum phenomena with spiritual or metaphysical ideas that lie outside the testable realm of science. While the connections to Eastern philosophy are intellectually fascinating, many physicists caution that they are analogies, not evidence. They worry that this mystification of quantum mechanics obscures its real mathematical substance and provides a veneer of scientific legitimacy to untestable claims about the power of the mind. So, where do these critics believe the true solution lies? The overwhelming consensus among working physicists is that the paradoxes of quantum mechanics, including the measurement problem, are not proof of consciousness's power, but are instead signposts pointing toward the limits of our current theories. They are gaps that future physics will fill. The most promising path forward is thought to be the quest for a theory of quantum gravity, a framework that successfully unites the world of the very small, described by quantum mechanics, with the world of the very large, described by Einstein's general relativity. It is at this tumultuous frontier that the true nature of the quantum to classical transition may be revealed. Proposals like Roger Penrose's objective reduction, which ties collapse to gravitational effects, represent one such attempt to find a physical trigger utterly independent of any observer. Others place their hopes in deeper modifications of quantum theory itself, or in cosmological models where the entire universe's wave function behaves in a way that makes definite outcomes inevitable. The key point is that these are all physical proposals. They seek to explain the definiteness of the world using the language of fields, forces, and space-time geometry, not the language of mind and awareness. For the skeptic, the history of science is a long and successful campaign to remove human-centered illusions from our understanding of nature. They are betting that the mysterious observer will eventually be explained away, just as the vital force once thought necessary for life was explained by the complex chemistry of biology. The role of consciousness in this future theory will be what it has always been, a magnificent and intricate phenomenon that the universe produces, not a fundamental force that the universe requires to exist. So, where does this leave us in our grand quest? We are caught between two breathtaking but seemingly irreconcilable visions. A universe that seems to demand our conscious participation to become real, and a universe that stubbornly insists on its own independent, objective existence. The stalemate between these views and the very paradox of the observer itself may not be the final word, but rather a signpost pointing toward the next great frontier in physics. The resolution likely lies in a theory that has so far eluded our greatest minds, a seamless union of the two most successful but contradictory frameworks we have: the quantum description of the tiny and Einstein's general relativity, which describes the cosmos at its largest. This holy grail, a theory of quantum gravity, promises not just to explain black holes and the Big Bang, but to finally answer the deep philosophical questions about the role of the observer in the architecture of reality. To understand why this unification is so crucial, we need to appreciate the fundamental clash between these two pillars of modern physics. Quantum mechanics, as we've seen, is built on a foundation of probability, uncertainty, and potentiality. It describes a world that is fuzzy, non-local, and where definite properties are not inherent but are realized through interaction. General relativity, on the other hand, paints a cosmos of breathtaking certainty and geometric elegance. It describes gravity not as a force, but as the curvature of a smooth, continuous, four-dimensional spacetime by mass and energy. In Einstein's universe, reality is perfectly deterministic and local. Every event has a specific cause in its immediate past. You can see the problem immediately. Quantum mechanics needs a fixed background stage, a spacetime, on which its probabilistic dances can unfold. But general relativity says that spacetime itself is the dynamic, malleable lead actor in the cosmic play. It's as if one theory requires a solid, unmoving canvas, while the other insists the canvas is itself a swirling, shifting part of the painting. This incompatibility becomes catastrophic in extreme environments where both theories must apply simultaneously, such as the infinitely dense singularity at the heart of a black hole or the first fleeting moments of the Big Bang. Our physics simply breaks down. It is within this monumental struggle to marry the fuzzy with the smooth, the probabilistic with the deterministic, that the mystery of the observer will likely be resolved, not as a philosophical add-on, but as an intrinsic feature of a deeper physical law. Several brilliant pathways are being pursued in this quest, each offering a radically different perspective on the nature of space-time and, by extension, the nature of observation. Let's start with one of the most well-known, string theory. This approach proposes that the fundamental constituents of reality are not zero-dimensional points, but incredibly tiny, vibrating one-dimensional strings. The different vibrational modes of these strings, like the notes on a violin string, give rise to all the particles and forces we see, including the hypothetical graviton, the carrier of the gravitational force. In this view, spacetime is an emergent, secondary phenomenon, a kind of stage that arises from the collective behavior of these strings. If spacetime itself is not fundamental, then what does that mean for the observer? The act of observation has always been defined as an event within spacetime. But if the stage itself is a derivative concept, then the observer might have to be redefined in a more abstract, fundamental way, perhaps as a property of the interactions between these underlying strings. Some interpretations of string theory, particularly those involving the holographic principle, suggest that all the information contained within a volume of space can be encoded on its boundary. This dizzying idea implies that our apparent three-dimensional reality, complete with its observers and observations, is a projection from a two-dimensional information field. In such a universe, the observer isn't a special entity that collapses reality from the outside, but is itself a pattern within a vast, cosmic computation where information is the only true currency. A very different but equally compelling approach is loop quantum gravity. Unlike string theory, which aims to be a theory of everything, loop quantum gravity focuses squarely on quantizing spacetime itself. It proposes that space is not smooth and continuous, but is woven from a fabric of tiny, finite loops, often visualized as a network of intersecting threads or a spin foam. Space is granular at the Planck scale, much like a digital image is made of discrete pixels. Time, in this framework, might also be emergent from the changing relationships between these loops. This has profound implications for the observer problem. In a universe where space and time are discrete and relational, the very concept of a continuous, flowing now in which an observation occurs might be an illusion. An observation could be a discrete event in this network, a fundamental process where the geometry of spacetime itself is updated. The transition from quantum possibility to classical fact would not be a mysterious collapse, but a natural, physical transition within the spin foam, governed by the dynamics of the loops. This could provide a purely physical resolution to the measurement problem, entirely removing the need for a conscious observer. The definiteness of the world would emerge from the underlying granularity of space-time, much like the smooth appearance of a television screen emerges from the rapid switching of its individual pixels. A third and philosophically fascinating contender is causal set theory. This approach is even more minimalist, suggesting that reality at its most fundamental level is nothing but a vast collection of discrete events connected by a web of cause and effect relationships. The smooth, four-dimensional spacetime of our experience is just a coarse-grained, approximate picture of this underlying causal network. In this view, what we call an observation is simply a specific type of causal relationship, an event where information is transferred from one part of the network to another. The flow of time itself is an illusion generated by the sequential unfolding of these causal links. This perspective elegantly reframes the entire discussion. The universe is not a thing that is, but a process that happens, and we, as observers, are not external entities looking in, but are complex, self-referential substructures within this vast causal web, particular patterns of events that have the capacity to reflect upon and model the rest of the network. Our observations don't create reality, they are a part of the reality-creating process itself, one causal interaction among countless trillions. As these theories mature, a common theme is emerging, one that brings us full circle to John Wheeler's visionary "it from bit." The future of physics seems to be converging on the idea that information is more fundamental than matter or energy or even space-time. In this new paradigm, particles, forces, and the geometry of the cosmos are all seen as manifestations of underlying informational relationships. If this is true, then the role of the observer transforms completely. An observer is no longer a mystical collapse trigger, but a complex information processing system that is itself part of the universal computational network. The transition from the quantum to the classical world is not a collapse, but a specific kind of information theoretic process, the point at which quantum information becomes amplified, copied, and irreversibly embedded in the environment, a process known as quantum Darwinism. In this view, the reason we all agree on the position of the moon is not because a conscious mind is looking at it, but because the information about the moon's location has been redundantly imprinted onto countless photons and other particles, making it available to any observer who cares to look. The universe is defining itself through a constant, democratic process of information exchange. We, as observers, are not the kings who decree what is real, but the citizens who participate in a shared, consensus reality built from the ground up by countless informational interactions. The search for quantum gravity is therefore a search for the ultimate operating system of this cosmic computer, a set of rules that will finally explain how the rich, definite world of our experience emerges from a fundamental realm of pure relational information. And so we find ourselves at the end of an incredible journey, a voyage that has taken us from the reassuring tick of a cosmic clock to the shimmering, creative potential of a universe that seems to respond to our very gaze. We began with the solid, predictable world of Isaac Newton, where planets followed their paths with unwavering certainty, and reality was considered an absolute external stage, indifferent to whether anyone was in the audience. Then we plunged into the quantum realm, where the very act of looking became a force that collapsed a haze of possibilities into a single, definite fact. We've grappled with cats both alive and dead, with friends in a superposition of memories, and with infinite branches of reality splitting with every possible decision. We've seen how the entire cosmos appears fine-tuned for life, and how life, in turn, through the act of observation, might be what gives the cosmos its final, definite form. This is the grand, participatory dance we've uncovered, a universe that is not a pre-recorded film, but an interactive, ongoing creation, and we are not merely passive spectators, but essential players in the story. The line between the inner world of our consciousness and the outer world of galaxies and atoms has become profoundly blurred, suggesting that the nature of reality itself might be inextricably linked to the act of perception. This radical shift in perspective carries a weight of responsibility that is both humbling and electrifying. If our observation, our attention, and our conscious interaction with the world play even a small role in crystallizing reality from the quantum potential, then our place in the cosmos is transformed. We are no longer accidental tourists in a vast, indifferent machine. We are collaborators, co-creators in a magnificent, unfolding process. Every moment of focused awareness, every question we ask of nature, every act of mindful perception is not just us learning about the universe, it is the universe coming to know itself through us. This idea, which once belonged solely to the realms of philosophy and mysticism, now finds a strange and compelling echo in the language of our most advanced science. It invites us to see our lives not as isolated events, but as integral threads in the fabric of a conscious, self-aware cosmos, which brings us to a final and deeply personal question. If we truly are participants in this grand cosmic process, if our perception and intention help to shape the reality we all share, then we must ask ourselves, what kind of universe do we want to help create? This is not a question with a single scientific answer. It is an invitation to reflect on the power of our own awareness. Do we want to contribute to a universe defined by curiosity, by wonder, by compassion, and by a deeper seeking for truth? The quality of our attention, the focus of our curiosity, and the intention behind our observations might, in ways we are only beginning to fathom, ripple outwards and influence the very reality we are measuring. This is perhaps the ultimate implication of our journey, that the quest to understand the universe and the quest to understand ourselves are one and the same. The outer cosmos and the inner cosmos are reflections of a single, unified mystery. So we leave you with this thought, not as a conclusion but as an opening. The conversation about the nature of reality is far from over. In many ways, it is just beginning. We want to hear your voice in this conversation. What does this mind-bending idea inspire in you? What are your wildest thoughts, your most profound theories about our role in this participatory universe? Do you lean towards the cosmic solitude of the many worlds, or the intimate creativity of the conscious observer? Share your perspective in the comments below. Let's continue this exploration together, because the most exciting discoveries are often the ones we make as a community, united by curiosity and wonder. And if you're eager to keep questioning the fabric of reality with us, make sure to subscribe and hit that notification bell. This is just one of many deep dives into the mysteries of existence, and we can't wait to see what we uncover.